Happy snow day, everyone. I thought that I would go over this quiz on rotational motion via screencast so that everybody could see how these problems are done before the test tomorrow on Wednesday. Okay, so the setup of this problem is that there was a long, thin rod that had mass, and it was fixed about an axis that's a quarter of the length down the rod. This total length of the rod is 4d, and so d is the distance from the left side to the axis, and then 3d is from the axis to the right side. Also on the right side is a bob of mass mb, mass of the bob. So it's like there are two different objects, a rod with a bob stuck on it, and the system is free to rotate about this axis. So one asks, calculate the moment of inertia of the rod alone without the bob about the hinge axis. So here's the axis that it's rotating around. This is a parallel axis theorem question. You need to start by knowing that the moment of inertia of the rod through the center of mass is 1/12 ml squared. L is the length of the rod. What is the length of the rod? Well, it's 4d. You'll forgive, please, these numbers that I've written on my version here. Those are for allocation of points. And so 1 point was allocated for knowing that the length of this rod, L, is 4d. We're supposed to answer in terms of d. Okay. And now, let's see. That is the moment of inertia of the rod about its center of mass, but the axis is not the center of mass axis. It's at a distance d away from the center of mass axis. This diagram indicates that here's the axis there. The center of mass is halfway through. So if this distance is d, this distance is also d. So the h in the parallel axis theorem is the value d. So this h equals d. 1 point was allocated for that. So that means that the total moment of inertia of the rod about the hinge is 7/3 mass of the rod times d squared. Okay, now treat the rod plus bob as one object. What is the moment of inertia of that object about the hinge axis? So the moment of inertia of the whole object will be the sum of the moment of inertia separately of the rod, which we calculated in number 1, plus the bob. So 7/3 mass of the rod times d squared plus, okay, now how do we get the moment of inertia of the bob about this axis? Well, it's like a point mass with mass mb, and it's at a distance 3d from the axis. The moment of inertia of a mass about the moment of inertia of a point mass about an axis is ml squared, and in this case it's mr squared, and in this case r, the distance from the axis to the point mass, is 3d. So I square the 3d, and so the total moment of inertia of the rod plus bob is 7/3 mass of the rod d squared plus 9 mass of the bob d squared. Calculate the total torque exerted by gravity on the rod plus bob object. At this point, I'd like to talk about a common error that was made in number 1, and I guess number 2. It was fairly common for people to say, oh, this is one object here to the left, and I'll find the moment of inertia of that by treating it as an object that's located here. And then this is a separate object here to the right, and I'll treat this as one object located at its center of mass. You can't do that for the purposes of calculating moment of inertia. You can't treat an object that extends through space as a point mass located at the center of mass. The reason you can't do that with moment of inertia is because of the r squared term. You can treat an object as being located at its center of mass for the purposes of calculating gravitational potential energy. We had a problem like that in this unit. You can treat it as an object located at its center of mass for the purposes of calculating torque, as we will do number 3. But you can't just treat an object as a point particle located at its center of mass for the purposes of calculating moment of inertia. But you can for the purposes of calculating the torque. So the torque, the gravitational torque on the rod comes from imagining that the gravitational force on the rod is acting at the center of mass of the rod. The force of gravity on this whole rod can be thought of as acting there at a distance d from the axis. So in the RF sine theta is 1. The distance from the axis to the location of the force on the rod is d, and then the gravitational force is g times the mass of the rod. Okay, now the torque by gravity on the bob, you can say that the distance from the axis to the bob is 3d, and the gravitational force on the bob is the weight of the bob that's mbg. And so the torque on the bob is 3d mbg. You add them together to get the total torque of the object. This question asks, what's the angular acceleration of the rod plus bob object at the instant shown? And as it drops, will the angular acceleration increase, decrease, or stay the same? The angular acceleration comes from the torque divided by the moment of inertia of the object. So the answer to number 3 divided by the answer to number 2. And that's it. As the object falls, look what happens in this extended free body diagram. Here, well, I guess here's what won't change. The gravitational force on the rod plus bob won't change, and the radius of the various forces acting will not change. What will change is the angle that the gravitational force vector makes with the r vector from the axis to the location where the forces act. Here, the angle between r and f is 90 degrees, so the sine of it is 1. That's as big as the sine of that angle will ever get. Here, the angle will be like some obtuse angle, and the sine of this angle will be less than the sine of this 90 degrees. So the torque caused by gravity decreases, and the angular acceleration decreases with time. Okay, this I have a little bit of trouble explaining in words. Thumb in the direction of A, index finger in the direction of B, put your third finger, your middle finger, at a right angle to both of them. These are the answers. Up, up, into the page, and the cross product of these two vectors is 0. So that's physics class for today. Happy snow day, everyone, and see you tomorrow.